examples of balancing redox reactions using oxidation number method and half reaction method. These are the steps involved in balancing redox reactions using the oxidation number method. Let us begin with this first example. Our first step is to go through each element and determine its oxidation number. Be careful with this chromium over here. It is a positive 6 because negative 2 times 7 is negative 14 and 6 times 2 is positive 12. And when you add positive 12 with negative 14, you get negative 2. Our next step then is to figure out which element is being oxidized and which element is being reduced. If you look at the chromium, the oxidation number goes from a positive 6 down to a positive 3, and so it's reduced. It gained 3 electrons per chromium atom. However, this ion has 2 chromiums in it, so it actually gains 6 electrons in this reaction. We have to keep that in mind. Where is the oxidation happening? Is it oxygen? No. The oxidation number for oxygen hardly ever changes. Will it be hydrogen? Probably not. There are no hydrogens on the right side as of yet, so it must be carbon. Carbon goes from a negative 2 to a positive 4. That's an increase of 6. So therefore it lost electrons. There are 2 carbons in this molecule, so it actually lost 12 electrons. We need to balance the number of electrons gained with the number of electrons lost. So what we're going to do is we're going to try to make them equal to each other. We want them to have 12 electrons gained and 12 electrons lost. So in order for us to do that, we have to put a 2 in front of the dichromate. Then we balance the right-hand side by inspection. Since there are 2 dichromates, there are now 4 chromiums, and there are 2 carbons that we need to account for on the right-hand side. So we put a 2 in front of the CO2. So at this point, we are going to try to balance the oxygens. What we need to do here is to count how many oxygens there are on both sides of the equation. So on the left-hand side, we have 2 times 7, which is 14, plus 1 more makes 15 oxygens. On the right-hand side, we have 4 oxygens because we only have oxygens in the carbon dioxide, and there are 2 molecules of it. So we have 15 oxygens on the left side and 4 oxygens on the right side. We need 11 more oxygens. The way we add oxygens is by adding water molecules. The next step is to count the number of hydrogen atoms there are. On the left-hand side, we have 6 hydrogen atoms, 5 plus 1. And on the right-hand side, we only have hydrogen atoms in the water molecule. So 11 times 2 is 22. Therefore, we need 16 more hydrogen atoms on the left-hand side. The way we add hydrogen is by adding hydrogen ions. We see that if this was an acidic solution that we're dealing with, we would stop here. This is our balanced redox reaction. We would have 2 dichromates, 1 ethanol, plus 16 hydrogen ions yields 4 chromium-3 ions, 2 carbon dioxides, and 11 water molecules. Right, that doesn't look balanced to me. So the first thing we're going to do is to check to see if the atoms are balanced on both sides of the equation. If you were to count the chromiums on both sides, you would see that there are 4 chromiums. The oxygens would be 2 times 7 plus 1, that's 15. And on this side, it's 2 times 2, which is 4, plus 11. That's also 15. The number of carbons is 2, and the number of carbons is 2. And the number of hydrogens is 6 plus 16, which is 22. And that is 11 times 2, which is 22. So the atoms are balanced on both sides of the equation. So you might be thinking to yourself, well, this is completely made up. We made these numbers up. How's this balanced? Well, the definitive way of checking to see if a redox reaction is balanced is by checking the charges. So you add up the charges on your entities, 2 times 2 minus, which is negative 4, and 16 positives, which is positive 16. That gives you a positive 12, a 12 plus oxidation number here. On the right-hand side, we have 4 times 3 plus, which is the 12 plus. Therefore, the charges are balanced and the atoms are balanced. And you did it right. If our reaction was occurring inside an acidic solution, if the reaction is occurring in a basic solution, what will we do then? If this redox reaction occurs in a basic solution, we cannot stop here. The reason is that there are still 16 hydronium ions inside the solution, and this makes it an acidic solution. So our next step is to add hydroxide ions to neutralize these hydronium ions. We are going to add hydroxide ions to both sides of the equation, however. So if there are 16 hydroniums, we add 16 hydroxide ions. So you can see that there are 16 hydrogen ions here with 16 hydroxide ions. The next step we're going to do is combine them to form 16 water molecules. So we're left with 16 water molecules, but we also see that there's 11 water molecules on the other side. So now we're going to cancel them out. 16 take away 11 is 5. So you have 5 water molecules on the left-hand side. At this point, we're going to say that we are done. This is how you finish balancing a redox reaction in a basic solution. But you still need to check that you did your work correctly. So again, we're going to check to see if we have the correct number of atoms. Times 2, which is 4, and there's 4. 4 chromosomes on each side. There are 2 times 7 oxygens, plus 1 more, that's 15, plus 5 more makes 20 oxygens on the left-hand side. 2 times 2 is 4, plus 16 is 20. There are 2 carbons, and there's 2 carbons. There are 6 hydrogens there, plus another 10, that makes 16 hydrogens. And there are 16 hydrogens there. Therefore, the atoms are balanced. We're going to now check to see if the charges are balanced. So there's a charge of 2 minus on the dichromate, and there's 2 of them. That makes a negative 4, a 4 minus oxidation number charge. On the right-hand side, we have 4 times 3 plus, which is a positive 12, and then we have a 16, 1 minus, which is a negative 16. That gives us a 4 minus, and that makes our charges balanced. The oxidation numbers method again, and this will be a reaction that takes place in a basic solution. Our first job is to determine the oxidation numbers. So in this example, I'm going to show you how we come up with some of these oxidation numbers. We always start off with oxygen has negative 2, and hydrogen has a positive 1. So in our lead here, we came up with positive 2. How do we do that? Well, the whole ion has a 2 minus charge, and hydroxide works out to have a minus 1 charge. You can see minus 2 plus positive 1 gives us a negative 1 charge. There are 4 hydroxides, so that means we have a negative 4 charge on this hydroxide side. So negative 4 plus 2 gives us a negative 2 charge. So lead must be a positive 2 charge. So if you were to continue on with this calculation, you would bring the negative 4 over to the right-hand side, and that would make X equals a positive 2, and that's how we came up with the oxidation number for lead. On the right-hand side, we see that oxygen has a negative 2 oxidation number, and there's 2 of them, so we have a negative 4 on the oxygen side. That means that the lead must be positive 4. Again, we can do this algebraically and say that X plus 2 times negative 2 equals 0, because it has to have a neutral charge here, and X is equal to 4 when you bring this negative 2 times 2 over to the other side. We have the oxidation numbers. We're going to try to figure out which one's being reduced and which atom is being oxidized. So I'm going to zoom in on lead here. We have a positive 2 oxidation number turning into a positive 4 oxidation number, which means it's going up, and that means that it's being oxidized. It's going to lose 2 electrons per lead atom, and for the whole formula unit here, this whole ion, it still only loses 2 electrons because there's only 1 lead inside this ion. Chlorine, on the other hand, goes from a positive 1 to a negative 1, so it goes down. So it's being reduced, and it's gained 2 electrons per chlorine atom. And again, this ion only has 1 chlorine atom in it, so it gains 2 electrons. So because the number of electrons gained and the number of electrons lost are the same, we do not need to add any coefficients to the front of these two reactants. So because the number of electrons gained equals to the number of electrons lost, we don't need to add any coefficients in front of the two reactants. We can just put a 1 in front of both of them. The reactant side is already balanced. So now we're going to balance the right-hand side by inspection. Again, it is already balanced. Next, we're going to balance the oxygen atoms. There are 5 oxygen atoms on the left and only 2 on the right. So what we're going to do is we're going to add 3 more oxygens by adding 3 water molecules on the right. So now we have too many hydrogen atoms on the right-hand side. We're going to count that just to make sure. We have 6 hydrogens on the right-hand side and 4 oxygens on the left-hand side because of this hydroxide. So we are short 2 hydrogens on the left. We're going to add 2 hydrogen ions on the left to balance out the hydrogens. The next step is to remember that we're dealing with a basic solution, and so we have to add hydroxide ions to balance out, to neutralize the hydrogen ions. And we're going to add hydroxide ions to both sides. There are 2 hydroxide ions added because there's 2 hydrogen ions in there. And whenever we have hydrogen ions and hydroxide ions together, we form a water molecule. So there's 2 water molecules formed from these 2 ions there. Next, we're going to cancel out the water molecules that appear on both sides, and we're going to have a remainder of 1 water molecule on the right-hand side. So that is that, and now it's time to check. And we're first going to check to see if the atoms balance, and they do. Next, we're going to check to see if the charges balance. A 2 minus on this ion plus a 1 minus on this ion makes a 3 minus on the left-hand side, and a 1 minus on this ion and a 2 minus on this ion adds up to 3 minus on the right-hand side. Next, we are going to do an example using the half reactions method. The half reactions method steps are listed here. Here's our example for our half reactions method lesson. We have a dichromate plus a chloride ion, giving us a chromium ion and a chlorine molecule. This redox reaction takes place in an acidic solution, and we're going to balance this using the half reactions method. First, we're going to determine the oxidation numbers. And there they are. Next, we're going to determine the oxidation and reduction half reactions. So we can see that chromium is being reduced as it goes from +6 down to a +3. That's a reduction of 3 electrons. And the chloride ion is oxidized by 1 electron. So there's our reduction half reaction and our oxidation half reaction. Our next step is to balance the elements that are not oxygen. So we have chromium here, we need to have a 2 there, and we have chlorine here, and there's our 2, so it's balanced. Next, we're going to take our oxygens and balance them for each half reaction. So these are 2 separate half reactions. The reduction half reaction has 7 oxygens on the left-hand side. We're going to need to add 7 waters on the right-hand side. The oxidation half reaction does not have any oxygens, so we don't need to add water. Next, we're going to balance the hydrogen ions. There are 7 times 2, that's 14 hydrogens on the right-hand side of the reduction half reaction, so we're going to add 14 hydrogen ions on the left. The oxidation half reaction has no hydrogen. Next, we're going to balance the charges on both equations by adding electrons. So to do that, we're going to need to count the charges on both sides of the equations. The charges here are 2 minus and 14 plus. That makes a 12 plus on the left-hand side. Here we have 2 times 3 plus, which is a 6 plus. That means we need to have a 6 electron addition on the left-hand side of this half reaction, because 12 take away 6 equals 6. On the oxidation half reaction, we see that the charge on the left-hand side is -2, and the charge on the right-hand side is 0. So we're going to add 2 electrons on the right-hand side. So now we're going to balance the equations by multiplying them with whole numbers to make the electrons even out. So we have 6 electrons on the left-hand side on the reduction half reaction, and we have 2 electrons on the right-hand side. This is perfect because you want to make sure that the electrons are on opposite sides of the equation. This is on the left-hand side of the reduction half reaction, and this is on the right-hand side of this half reaction. So what we do is we're going to multiply 3 times this whole equation to make this 2 electron turn to a 6 electron. So everything gets multiplied by 3, and this 2 will become a 6, this will become a 3, and that will become a 6. Now we see that the 6 electrons on the left-hand side of the half reaction for the reduction half reaction is going to be balanced out by the 6 electrons on the right-hand side of the oxidation half reaction. Now, we add the equations and cancel out the molecules that are the same on both sides. As it turns out, only the electrons are the same on both sides. And when you cancel them out, you bring everything down. Dichromate, 14 hydrogen ions and 6 chloride ions. And on the right-hand side, we have 2 chromium ions, 7 waters, and 3 chlorine molecules. So we're going to double check to make sure that the number of atoms and the charges on both sides are balanced. That's the end of this lesson on how to balance redox reactions using the oxidation numbers method and the half reactions method. Thank you for listening.